So you might be actually knowing this title because I talked about it last year, but we continue to work on it. So this is work with Bernd Peisan. We continued to work on it, and I actually have some new stuff to report. And I already gave a short version of this talk at eCoop last week. So background is, we use a virtual machine interpreter with code copying, and you know it as gforth. And in this, as you will see, in this virtual machine interpreter, every virtual machine instruction increments the virtual machine instruction pointer. And the question is, how relevant are IP updates for performance? And the answer is that it actually is quite relevant on some programs. And how do we find that out? We implement an optimization, or several optimizations actually, and compare the performance with and without this optimization. And here we have, first of all, why do I talk about optimizing interpreters at all? Shouldn't I just go to JITs like several other people have done? And here we see gforth with the new optimizations in red against some other forth systems, SwiftForth, VFX, in light blue and violet. And you can see that the gforth performance is comparable to that of SwiftForth with the new fix that we talked about yesterday. And so it actually is, I think it is relevant. So we also see that gforth is competitive. So for a few benchmarks, there's also C versions of that benchmark, and on these gforth is comparable to GCC with -0.0. So running example is the inner loop of the Sieve benchmark. Here's the forth source code. And for those who don't know forth, this is some similar C code. And here's the virtual machine code of gforth, which is very similar to the source code actually. And one thing I should mention is we have in the virtual machine code, we have instructions with immediate arguments, like lit has the immediate argument 0 here, which corresponds to this 0. And the parent plus loop has an immediate argument start, which is a pointer back to the start of the loop. And this corresponds to this plus loop here. So the baseline, so where we started from before our optimization is a code copying interpreter with static stack caching. And here's the virtual machine code again. And here's the native code. And for each virtual machine instruction, we have a code snippet, and we concatenate the code snippets. So for lit, we have this code snippet. For I, we have this code snippet. For C-store, we have this code snippet, and so on. You see in blue, you see the IP updates, which is what the present talk will be about. The gray stuff is the payload, which is the actual program we are interested in. So the IP updates are just overhead. We also have in green references back to the virtual machine code. And that's why we need the virtual machine instruction pointer. So IP is the virtual machine instruction pointer. Because we still have references into the virtual machine code, we need to maintain it. And here in magenta, we have control flow. So at the end of this loop instruction, if the branch is taken, the virtual machine branch is taken, we actually have to set the IP back to the start and actually also perform a jump, an indirect jump through this lid here to here. Okay. So the question is, I am calling it an interpreter, but there might be different opinions about that. So one opinion is it's a JIT compiler because it copies native code. The reason why I think it's an interpreter is because it's portable. GCC generates the code snippets. We work on several architectures because of this. There's a fallback option to a threaded code interpreter. So if there are some assumptions that are needed to make this code copying possible, if these assumptions do not hold, we can jump to the original places where the code snippets come from, and it will perform threaded code interpretation without code copying. We still need the virtual machine code, so we still need this stuff, unlike a native code compiler, unlike a JIT compiler. We need it for immediate values, the green stuff, and we need it for control flow, the magenta stuff. And because we still need the VM code, we also still need the VM instruction pointer. So next to our core question, what is the performance impact of the instruction pointer updates? First, and here we see the latency stuff. The latency of the dependencies of the instruction pointer updates. So this add, and these numbers are for a Tiger Lake, Intel Tiger Lake processor. So an add is 1 cycle. So all these adds are 1 cycles, which is for all these adds are 5 cycles. And then here we have a load, which is 5 cycles latency. And here we have a move, which has 0 cycles latency. So the whole cycle here takes 10 processor cycles overall. So if we have a large number of iterations, each iteration takes at least 10 cycles. And this is actually limiting our performance, as we will see. So what can we do about it? The first is we can combine instruction pointer updates for cases where so in most of these instructions, the instruction pointer is not needed, and we can actually eliminate the instruction pointer update for them and eventually replace this one with one that has a large instruction pointer update. This is done by having another code snippet or a bunch of code snippets for instruction pointer updates of different span. And here we eliminate this part of the code snippet, and instead of having this one here, we have one which updates by 40 bytes. And why can't we eliminate this one too? That's because we need an instruction pointer update here. Why can't we eliminate, we need a current instruction pointer here. We cannot eliminate this one because we need a current instruction pointer here. So, but we've reduced it from 10 cycles to 7 cycles in this dependency cycle. The next point is, we have we needed this instruction pointer update because we need the instruction pointer to be up to date here, but we can actually make various versions of this lit instruction which work with different offsets of instruction pointers. So instead of having the one that assumes that the instruction pointer points to here, we can, to here actually, we can have one that points to here, and this is what's happening here, and then we don't need this instruction pointer update here. And that's our next optimization. We could actually do the same for the parent plus loop, but the problem, of course, with all these code snippets is that the number of code snippets we want to produce is limited, and so we only do it for the most common ones, and also only a certain number of them. Parent plus loop is a relatively rare instruction, virtual machine instruction, so we don't have different versions of that. So we actually need this instruction pointer here, but of course, because we have eliminated this one, we need a different update here. And this is needed because we access the instruction pointer here. So the next thing is I noticed that there's, and we tried out another optimization that I will come to back later. But I noticed that the other optimization was still better than what we get for this. And the reason is these 5 cycles. So I thought, can we do something for getting rid of these 5 cycles and reducing it? And the idea was to actually set the instruction pointer to the target of this branch, so to here, and then have if the branch is taken, branch to it. If it's not taken, afterwards we will have an instruction pointer that corrects for it, an instruction pointer update that corrects for it. And that's what's happening here. And so instead of having this instruction pointer update that updates the instruction pointer to here, we conceptually have here an instruction pointer update that sets the instruction pointer to here. But the actual case is that the instruction pointer is still here, so we would need to update by 0 bytes, and that's optimized away. So in this final optimization, we have actually 0 instruction pointer updates here, and 0 which takes 0 cycles overall in latency. This is, of course, a best case. There are cases which are not so great. So another optimization. So we go back to the start, where we still have here 10 cycles of total latency. Another idea is, instead of loading the start from an immediate argument of plus loop, we change plus loop to actually, so we take the do plus loop, and such that the do part pushes the return, the start address of the loop, and the plus loop branches to it. So it pushes it on the return stack. And that's what's happening here. So in the parent plus loop, we load the new instruction pointer from the return stack. And this, the nice thing is, this doesn't depend on the old instruction pointer, so on the instruction pointer of the current iteration. So we have basically, this breaks the cycle. So we no longer have a cycle. Every we have this chain with latency 9, but this chain ends, and in the next iteration we will create another chain, which can, on modern hardware, can run in parallel to this chain. So this also eliminates the problem with the dependencies. So performance. Here we see speed up over the baseline, which is the G4 version we started with. The first shown in black is this loop optimization that I presented last, because the loop optimization is the one that always we implemented it a little bit after the C optimization, and it's what we see is that for some benchmarks it produces very good results, and that's and better results than the C optimization and the CI optimization. So it's also the I always thought, so okay, there must be something else I can do, and gave the motivation to continue with the B optimization. So one other thing we see is, for some benchmarks the speedups are great, and for other benchmarks they are not so great. And this is typically for loop dominated benchmarks, the speedups are good. For typically fourth code with many calls and returns without loops in these words, the speedups are not so great, because the return also breaks any dependence chains of instruction pointer updates. Some other thing we see is that we have some cases in which here we have also C plus B without the immediate optimization, and we see there are cases where CI is better than CB, and other cases where CB is better than CI. But in any case, CI and B is best. Overall. Here we see how this works across different processor generations. To the left we have Intel P cores, performance cores, the big ones, and to the right we have Intel E cores, the efficiency cores as they are called. And what we see is that the tendency is that the optimization gets more effective with the processor generation, with one exception. The newest, the Golden Cove is from 2021 or something like that. Golden Cove actually, the optimization gets less effective, or it gives less speed up at least. And the reason for that is that Golden Cove can do add with a constant in 0 cycles. So the whole C optimization is already done in hardware by Golden Cove. But for others it's still quite good. And one thing about the whole development that's interesting is we looked at this kind of stuff 20 years ago. I did some preliminary measurements, and they were not very exciting. So I thought I'm not going to investigate this more deeply. A few years ago, I measured it again, and then it looked much more promising. So last year I investigated this, and these speedups, they actually exceed my expectations. So I also expected at the time that as processors get wider, the additional instruction, the reduction in instructions from this optimization would become less of a would become less relevant, and therefore I would see less performance difference from this optimization. And I didn't expect that latency would play a big role, but it does. So, conclusion, virtual machine instruction pointer updates can be a performance bottleneck, and we can optimize these updates by combining them, and we can increase the effectiveness of this C optimization by having multiple immediate operand variants of the virtual machine instructions. And we can also optimize the branches to branch to the adjusted instruction point and eliminate the long latency of the load in this way. And another option is to cut the dependencies in loops by loading the loop start address without using the instruction pointer, the virtual machine instruction pointer. One thing I wanted to say about this, in Forth I can do the L optimization only for counted loops and not, I don't see a good way to do it for channel loops, but in other programming languages that's also an option. So the results are speedup factors of more than a factor of 2 on loop-dominated benchmarks on some processors, and that's because the instruction pointer updates are the critical path. And on other benchmarks, I see smaller speedup factors, especially on call-dominated benchmarks like 1.1 to 1.3. And this is because in that case, the number of instructions, the resources used by these instructions are what causes the beneficial effects, and that's not so big. And if you want to read the paper, it has been published at eCoop, and here are the URLs, and the DOI is digital object identifiers.
Thank you, Anton. What a lot of work, Anton.
It was.
Stephen, wait for me.
Sorry?
I'm rushing with my accelerated knee. Optimize knee.
Oh, sorry, my wake people up.
What am I supposed to do?
Just talk. Don't press.
Okay. Have you done this for any other processors than x64?
Yes, we have done it also on ARM, and I can show you stuff for example, very nice results on the Apple M1 on the Firestorm.
Oh, right.
Yeah.
I'd like to see those.
Yeah, but I don't have it in this slide, so I can
Okay.
show it to you offline.
Do you think that the other CPUs are going to have this horrendous variation in performance over several generations, or do you think people have learned from x64?
Oh, you see the same thing on ARM too. So we have measured a number of ARM CPUs, and of course, I mean, the wider they get, the more benefit they get from this optimization.
Okay, because that's going to be a topic of interest for us. Thank you very much, Anton.
So, Anton, I mean, it's classic in a Forth system for there to be an instruction pointer, the Forth IP, which differs from the program counter. But when we implement, we can usually choose perhaps a particular register to be the Forth IP. What's the Forth IP in your system?
As it happened, I looked at it this morning, and it is R13. But I mean, this is what GCC chooses. So
That's what so it chooses a register.
yeah.
But the register set is fairly symmetric, is it? So it's pretty arbitrary choice.
It's somewhat arbitrary. There are some slight thingies with kinds of, I think R13 has a special restriction on not being having an addressing mode without offset. But I mean, this is just minor stuff.
Thank you. Thank you very much, Anton.